So today we will continue to talk about digital signal theories. So previous chapter signals are continuous, which is not that useful when we work with digital computers because they cannot work directly with continuous signals. When signal enters a computer, it needs to be discretized. So there are two ingredients of discretization, which is sampling and quantization. So if you ever look at the file information for digital audios, you may see something like the following. I don't know that command. Channel sample rate precision. So sample rate tells you about sample rate, and the precision is about quantization. So how many bits are used for each sample, I think. And channel tells you how many signals are contained in the file. This section introduced discrete sampling, the process of summarizing a continuous signal by discrete sequence of sample values. Yeah, this chapter covers the basics because it's a very deep topic. Yeah, sampling is more important than quantization. Yeah. So let's start talk about basics, sampling period and rate. So sample period is denoted by TS, which I think it's more common to denote by period by uppercase T, but this book used lowercase t for like period of wave too. So yeah, which must be a positive number, measured number of seconds between samples, near fractional number allowed. So like this. In slight abuse of notation, we use square bracket with index n to indicate a discrete signal, and parentheses with time t to denote continuous signal, so we get this following. By convention, we use uppercase N to denote the total number of samples. Oftentimes, it's more convenient to work with the sample rate, which we denote as the inverse of the sample period. Also, like this book uses a very interesting way of the. Pardon, I can't hear anything, but it's really loud.
I'm sorry. Yeah, I think I fixed my mic.
Oh, it's good now. Yeah. Yeah. So, just I feel like this unit is pretty interesting. Like, I think last chapter we also talk about because like for other sources, they probably will just say inverse second or like hertz. But in here, like they explicitly say it's a samples per second. Just an interesting, more detailed convention, I guess, than the typical source. Note that the sampling rate can always be converted to a sample period, and vice versa by taking reciprocals, resulting in the following form of discrete sampled signal. Yeah. Yeah, notice this is not a x multiplied by something, but a function call. It's just a signal, but yeah, basically a function call. Yeah. So visualization. So signal which being sample is said to be discrete time signal, or sometimes just discrete signal, to distinguish it from continuous time signal. And we do not have sample values at non-integer indices. So it's often helpful for understanding to connect sample value to visualizations. When visualizing discrete time signals, we adopt convention of using step plots, just like the following, to emphasize the fact that signals have been discretized. Yeah, basically like the following. Yeah, for most practical application, we tend to have sample rates that are sufficient high to guarantee that a step plot and continuous plot looks visually identical. Or how does computer know how to plot a continuous plot? It's basically doing sampling, but yeah, just for demonstration purpose, we will use a low sampling rate, so it's easier to understand what's going on. And tone generation, we have enough knowledge, we can start to make sound. So we will generate a pure tone at 220 hertz, and then so a wave at frequency f0 is expressed as a function of time t by this following. Yeah, amplitude and phase, we can just add them, it doesn't matter. So we don't have an existing signal to sample, we can still sample from this idealized signal by substituting t equal to n divided by the sample frequency. Yeah, because, yeah, and compute the cosine values directly, like the following. Or in the code like this. Vectorization, this is just basically a Python thing, because running for loop in Python is very slow, but instead if you use those magical libraries, you get like much better performance, but because they will use all the tricks of native code. Yeah, not directly related to SIMD, but probably they will use SIMD under the hood. It's just basically a Python thing. So yeah. Aliasing. So we start to say something very relevant to graphics now. So in previous section introduced uniform sampling. Does this book ever talk about non-uniform sampling? I don't know. But anyway, yeah, which allow us to represent a continuous signal by a discrete sequence of sample values. But yeah, this idea comes with some restrictions. So aliasing is the name we give to phenomena where two distinct continuous signals x1t and x2t produce the same sequence of sample values when sampled at a fixed rate fs. So more specifically, we usually think aliasing in terms of pure tone, like this. Like think this is just because of convenience, because like like Fourier series and Fourier transform, you can express signals as linear combination of those sinusoidal functions. So as a result, we can just think about them, and if we understand the mass of those, then we basically understand the mass of the whole signals. So we don't need to consider the more complicated signals. Yeah. Anyway, so this definition gives a sample rate fs. Two frequencies f and f prime are aliased of each other if for some integer k, f prime equal to f plus k times fs. Yes. If sampled at rate fs, two wave x and y, which at frequency f and at frequency f prime, will produce identical samples. So we basically have those two waves. They look different, but because f and f prime, but they will produce identical samples. With a little bit of algebra, we can show that. I feel like I don't like how they present this on here, because this part is a definition and this is more like a consequence. So if it's me, I will put this outside this like green, this blue box, because it's kind of confusing.
Yeah, it is kind of more of an example. Yeah, it's kind of strange.
Yeah. Yeah, anyway, so this is something I didn't know for a long time. I only know aliasing as the visual artifact. I didn't know it has this deep meaning until much later. But yeah, this is a definition of aliasing. It's basically like high frequency and low frequency, two frequencies kind of produce identical samples. So frequency f prime is f plus some whole number multiple of the sample rate fs. This equation is known as aliasing equation. So it tells us how to find all the aliasing frequencies for a given f and sample rate. Yeah. Basically, with those samples, we can have this curve, we can have this curve, we can have this curve, etc. We don't know which is correct, basically. So yeah, I guess they use this very detailed unit, because then we can talk about this. So aliasing equation combine the frequency, which is cycles per second, with sampling rate, which is samples per second, scaled by some integer k. So follow out our earlier discussion of dimensional analysis, we need to assign some unit of k for this to be well defined. So f prime should also be the cycles per second. Yeah, because it's just frequency, not sample frequency. We should define k as cycle per sample, so that k times fs has unit cycle per second. So give unit to k help us reason about what it means intuitively. It means measure additional cycles between samples. Yeah, that's a good point. And yeah, if we just treat both of these as hertz, then we lost this paragraph basically. Why is aliasing a problem? Yeah, it's unavoidable consequence of sampling. There will always be frequencies that look the same after sampling. Yeah, the consequence is that once you sample that signal, you may not be able to determine the frequency of the wave that produces the sample you've observed. So the Nyquist-Shannon theorem suggests a resolution to this problem, but for now let's work toward a better understanding of why aliasing occurs. Negative frequency. Yeah, you may notice that we can have k less than 0 in the aliasing equation, which produce frequency like f equal to -4. What does that mean? It means, yeah, you can think of negative frequency as a frequency of point travel clockwise and rather than counterclockwise. Yeah, but the curve for that looks just like curve for the positive wave, at least for cosine wave. Yeah, for sine wave it's the flipped. Yeah, we'll later see how that's important. But yeah, anyway, why does aliasing happens? Yeah, in the previous section we sampled pure tone by using the following equation. To say why aliasing occurs between frequency f and f plus k times fs, we can plug the later into equation above and do some algebra. The key idea is this identity. Yeah, cosine theta plus 2 pi times an integer is just cosine theta, because we just go a whole circle basically, and that's why there's an integer here comes from because yeah, 2 pi an integer. So yeah, we can prove this by some algebra basically. We start from the aliased high frequency signal, and then we just expand, we do some cancellation and to here, and then 2 pi times k times n, because k and n are integer, this is integer, and then we can just remove that part. So we get this without the adjusted sampling frequency. And yeah, this is basically the original low frequency sample, which yeah, with this shows that these two frequencies produce the same sequence of samples regardless of k. Example, it is.
I think that's a good way.
Pardon?
Sorry. I was just going to say, I think that's a good way to explain it, that it's an additional number of cycles in between.
Yeah. Basically, that's yeah. It's just like this is a whole circle or like more cycles basically. So yeah, can always cancel in the cosine. Yeah, aliasing to this example, I don't know whether you can hear it. Can you hear it?
No, it's not.
So anyway, I guess the idea is like those two should be the same. So yeah, anyway. So Nyquist-Shannon sampling theorem. So the previous section we saw the aliasing occur between frequencies related by integer multiple of sample rate fs. Yeah, the bad news is that we can never avoid this. The good news is that if we are careful, we can ensure that aliasing effect does not corrupt the signal. That's what the Nyquist-Shannon theorem is all about, establish a condition under which sampling is okay. So sampling theorem is most easily understood in terms of pure tones. Well, most any signal you encountered in the world is unlikely to be pure sinusoid. It turns out that's just what I talk about. It's every continuous signal can be expressed as a linear combination of sinusoid. Yeah, I guess this explanation of what linear combination means basically. Yeah. So we can, that's why because of that we can reason about sampling just with one cosine function without all those other stuff. Note that we don't need to know the specific value for a and phi. This quantity will generally be unknown. And now this is a important concept, band limited signal. If it can be expressed as a combination, wait, sorry, I have something. I will be back soon. Sorry. Anyway, a band limited signal can be expressed as a combination of pure sinusoid whose frequency lies between some minimum frequency f minus and some maximum frequency. The size of this band of frequency is known as the bandwidth of the signal. Another way of think of band limiting is that any sinusoid with frequency that in this range basically has no, outside of this range has no weight in the combination that produce the final signal. The basic idea of Nyquist-Shannon theorem is that if sampling rate is sufficiently large compared to the bandwidth of the signal, then aliasing can't hurt us because it must have zero amplitude. So we can now formally state the sampling theorem, commonly attributed to Harry Nyquist and Claude Shannon, which is unfortunately because I think more people know that LLM stuff other than this person now. Yeah, but anyway, sampling theory is probably not first discovered by them, but some other people which unfortunately don't know how to marketing themselves, maybe. Yeah, anyway, so we actually state a simpler form of their theorem that's sufficient for our need. So if fx is band limited to the range, then any sampling rate fs greater than the f plus minus f minus is sufficient to prevent aliasing. That's a pretty interesting way of presenting that. Because in almost all the other sources I've seen is like using 2 times the frequency, but I guess because this book they allow like negative frequency, so they use this definition, but that should be equivalent. So pick any frequency f which have aliasing frequency of the form f prime equal to f plus k times fx of integer value k. Because the space between aliasing is at least fs and the bandwidth of the signal is at most fs, any aliasing frequency f prime must reside outside the frequency range of xt as depicted in the picture. Yeah. As a result, basically any aliasing frequency will be outside of the frequency range of band limited signal, so this should be, yeah, so the band limited frequency cannot alias each other. I also want to show you my note. Let's wait a second, because I draw some picture of this. Can you see it? It's pretty small, probably.
Yes.
Yeah, it's pretty readable.
Yeah, just basically just the idea of how, like a visual demonstration of how if you have like a sample rate small, then you can see in here you can sample like this, and then you can draw a smooth curve which is not the original signal, but then if you have a sampling frequency which is high enough, then this is impossible. You can perfectly reconstruct the original signal. It's a visual demonstration of what's happening.
On a sort of related note, have you ever heard of compressed sensing?
Compress something? I don't know.
Compressed sensing. It's so basically you can cheat the Shannon-Nyquist theorem by, instead of taking uniform samples, you can take random samples and then do some like linear algebra, just reconstruct the signal from fewer samples. So if you were to take random samples of the signal, then you can actually reconstruct it in some cases using fewer than twice the frequency, I guess, number of samples. If that makes sense.
Yeah, I don't know whether this book will ever touch non-uniform samples, but yeah, in graphics we almost exclusively deal with non-uniform samples. So yeah, but not exclusively. Like still sometimes do with like uniform on a grid, but a lot of time it's non-uniform.
Yeah, compressed sensing is really useful for like medical imaging, where getting more samples is like harmful to the patient. You know,
Yeah.
like in CAT scans or something. Anyway, that was a little bit of a tangent, but it's something I thought was cool.
Yeah, sounds cool. I will search this after the meeting. So, band limiting in practice. So, how do we ensure that signal is actually band limited? In hardware analog to digital converters, this is done by using analog circuit to filter the continuous signal and remove any frequency above the plus prior to sampling. If you ever see a tune knob on the electric guitar, the principle is much the same. But unfortunately, I don't understand guitar, so anyway, setting the bandwidth. At first glance, the Nyquist-Shannon theorem might suggest that set f minus equal to 0 and f plus to some reasonable maximum frequency. But unfortunately, that doesn't work because you have minus frequency at the plus frequency is basically the same. So yeah, because of the law of cosine. Or if it's sine, then it's just flipped or phase shift by minus pi. But anyway, so yeah, if we want to filter out negative frequencies, we must necessarily also filter out positive frequencies as well, because f and minus f are indistinguishable from each other. So yeah, so our band limit must be symmetric around 0. And yeah, this metric argument tells us that we must have f minus equal to minus f plus, and that's where in more common sources they use the 2 times f plus rather than just have this definition.
Yeah, that difference in frequencies is not very familiar. It's interesting. I've got to think about that a little bit more.
Yeah, because this one is much more familiar, at least for people who learned this content before. Alternatively, for fix the sample rate fs, the highest frequency that can be measured without aliasing artifact is fs divided by 2, also known as Nyquist frequency. Yeah, I guess audio is the important application of Nyquist-Shannon theorem. So we typically want f plus to be sufficiently large to capture the audible range, which for human is like this. So if we have a sampling rate larger than 2 times this, which is 40,000 hertz, then combining this with some other technical constraints resulting in the standard rate of this, which is still commonly used. Yeah, for a lot of audio file, you can still find that they have this sampling frequency. So quantization this is the last part. So, if we recall introduction to this chapter, we saw that digitized audio has two properties, the sampling rate and precision. So this section consider the precision, but what does it mean? Well, I guess because we are computer people rather than other engineers, we know this much better. Okay, this is just an explanation of binary. I think they start from decimal. Yeah, and then they talk about binary. Negative number. So this is just a two's complement. Yeah, two's complement basically. All right. So
Get your computer engineering crash course.
yeah, that's a very short crash course because I feel like if you don't understand this before, then this is probably too short.
Yeah, it's very, very short. Yeah.
Yeah. Oh, they even have floating point number. I will say how they explain that later. Anyway, so precision, also known as bit depth, refers to how many bits are used to represent each sample in a digital signal. Yeah. While we typically think signals as taking on continuous real values, computers quantize those values to be drawn from a fixed finite set of numbers. Yeah, because we sampling, we only like quantize the time dimension. We don't actually quantize the signal's value, but yeah, even for signal's value, computer don't have like infinite precision, so they need to do something with it. Yeah, high precision means that we have more distinct value. They can therefore more faithfully represent smaller differences. But however, doing so, yeah, just come with cost of more data basically. And interesting readers are encouraged to look into perceptual coding and lossy audio compression to learn more. This just reminds me of all the grammar business. I guess it's the same idea basically. And the effect of quantization. High precision values provide a good approximation of the original wave. But yeah, no quantization, 16 bits, almost cannot see the difference. 8-bit is a bit worse, 4 bits is significantly worse, 2 bits is just like stare now, and yeah, 1 bit's just become like this. Dynamic range. So this is actually some concept I don't know. Despite hearing about HDR all the time, I don't know what this means. So let's see what it means. Quantization reduces the number of distinct values that can be observed in a signal. Yes, rather than the full range of continuous values. Yes, say the voltage in the range like this, we instead divide up the range into pieces of constant quantized value. Yeah, for uniform quantization into n-bit integer, we have 2 to the n distinct number representing different values. So if q represents an n-bit quantized integer value, then we can map q into value q. Yes. Okay, this is just this above diagram. Yeah, this process is lossy. Yeah, in that not every continuous input value can be realized by a specific quantized number Q. And this fact raises many questions about how accurate the quantization process is. We won't go into details about quantization error, but one common use method to evaluate the quantization scheme is to measure its dynamic range. The ratio of the largest value to the smallest non-zero value. Measured in the decibels. I guess they use audio as an example, that's why. But anyway, typically the values in question are voltages, which you may recall from chapter 1 are proportional to sound pressure. And that intensity is proportional to the square of pressure. So to compute dynamic range for quantized voltage, we need to square them. I guess I need to revisit this part to understand more. But yeah, I can understand this part.
I think for the closest graphics touch point would be like the dimmest brightness to the brightest brightness for a pixel.
Yeah.
For the sound pressure, the minimum to the maximum range. So I guess kind of something like a contrast ratio of the dimmest to the brightest.
Yeah, that's I kind of get why like high dynamic range this concept comes from now, basically. Yeah, just from this definition, yeah. Yeah, anyway, I think I need to revisit this part to understand what they're talking about here. But anyway, note that dynamic range is not to be confused with signal to noise ratio, which is often reported as a measure of quantization quality, but it's a bit more involved, so this textbook will not talk about them, I think. But anyway, so with bit depths, we can have the following dynamic range. Yeah, basically n equal to 1, we only have 0 dynamic range, but then yeah, with improved bit depths, we have higher dynamic ranges. Yeah, floating point number. Note that floating point numbers are still technically quantized, but the quantization level is practically so small that we treat them as though they were not quantized at all. So I think this book will not explain like the intricacy of floating point numbers. Basically, it says yeah, good enough. Yeah.
Depending on who you ask, that could be a highly controversial statement.
Well, it depends on who is your audience. Basically, for us, we know it's because we sometimes need to deal with floating point number issues. But yeah, for intro to this kind of stuff, then yeah.
General audiences, definitely, yeah.
Yeah. Yeah, but anyway, yeah, dynamic range of floating point is insanely large, even for 32-bit. Like for 64-bit is even larger. But we cost something else basically. But there are no free lunch. There are just so many bits.
So this decibels is like it's the log of the ratio of the minimum value to the maximum value,
Yeah,
basically.
yeah.
Way that's defined.
Yeah, it's a log.
Okay.
Can simulate quantization numerically, yeah, by using the following function. It would be interesting to read through it, but yeah. You can't hear it, so I will just say the explanation. One thing you might notice from listening to the example above is that the lower quantization level have the same fundamental frequency but sound somehow brighter. Oh, that's interesting. That's because quantization introduces discontinuity to the signals. Oh yes. So we introduced the high frequency content just by quantization, basically. Interesting.
Yeah, because the square waves are step functions. Yeah,
Yeah.
that's cool.
Yeah, like 1 bit quantized, just jump abruptly between different sample values. Yeah, quantization in practice. So 16-bit quantization is the standard for compact disc quality audio. It suffices for many practical applications. 24 bits are also common, especially for music production or other applications with high fidelity requirements. Although audio data is stored this way, we don't usually worry about quantization when processing audio in a computer. Instead, we convert to floating point numbers. Yeah, do whatever and then quantize again. I think in
It's an
graphics we
interesting- Oops, sorry.
just in graphics we
Okay.
sometimes do something similar, like quantize normal vectors and then uncompact it in the shader back into floating point.
There's something that's a minor pet peeve of mine, and it is the handling of audio audio volume levels on mobile operating systems. This is an issue in both Android and iOS. They quantize to like 4 or I think it's 4 bits or something like that. So you're
Too low.
presented with you're presented with something that acts like a 0 to 100 or something, but you'll only actually get a change in volume when you go over a certain threshold that maps to whatever the 4-bit quantization level is. It's a pain in the ass, and you don't actually have the precision that it claims to have. And I have to assume that it's some kind of efficiency thing, that they're doing math with this, smaller precision something. Maybe there's a hardware optimization somewhere, but it's like, it depends on what hardware you're trying to play back on. But I had a Bluetooth speaker where that was an issue. Like the one bump down was too low, and then one above was like way louder.
But to be honest, most people probably don't care, or like they only have some intuitive feeling, but they don't know what's going on.
Yeah, they don't spend days thinking about, how am I going to try and fix this? And then, finding no solution, practically.
Yeah.
Anyway.
I actually think iOS has, in some cases, more precision than 16. I can tell you, I just checked, that they do have 16 volume levels using the plus and minus buttons on the rocker buttons on the side. However, I have fallen asleep to videos where I wanted it in my ear, but even the lowest volume setting was too loud. I didn't want to disturb someone I was in the same room as. So I went and, like, if you go into the control panel thingy and then tap the audio thing, you can dynamically slide it up and down. And I recall that if you do the rocker, you get a small bump, but not the smallest. You can use with your thumb and get a much smaller value, and it did have a correspondingly smaller output. Granted, this is the built-in speaker, not Bluetooth. It may be the operating system supports dynamic output for the built-in headphones, or the built-in headset speakers, and then quantizes literally everything else because hardware reasons, like you're supposing. Or
No,
whatever.
Maybe sorry. Maybe before we get to off topics, let's
Oh yeah.
stop recording.
Yeah, all right.